All right, class, let's talk about amplitude and equilibrium, which are both things that you have to understand about any oscillating system. First, let's tackle equilibrium. Equilibrium is the rest position of a system about which the oscillations occur. When we talked about earlier the block of wood resting in the water, equilibrium would be where the block is resting if nothing else is acting on it. So before it's bobbing up and down, just floating in still water, it's at equilibrium. If I push that block down, it goes underneath where it normally was resting, and then it bobs up above where it was resting. That oscillation about that point where it started is the equilibrium point. The equilibrium point is where it would be if nothing was acting on it. If you look at the pendulum example, if the pendulum's hanging straight downwards, right, before it's oscillating back and forth, right, hanging down directly under its pivot, that's its equilibrium position. If we pull the pendulum to one side and it oscillates back and forth, it is oscillating about its equilibrium position. So anytime we talk about an oscillating system, and this will carry over when we talk about waves, we're going to talk about the rest position or the equilibrium position. That's the point about which all the oscillations are occurring. If we look at the amplitude of the system, this also applies to oscillations. Anytime that something's oscillating, it's got to move some physical distance away from where it started, away from its equilibrium position. If you measure how far in meters it is away from its equilibrium position, this is what the amplitude of the system is. Amplitude, and I already mentioned that oscillating systems have energy in it. If we want to know how much energy is in an oscillating system, all we have to do is look to the amplitude, because the amplitude of a system, how far it's moving away from its equilibrium position as it oscillates, that amplitude is the energy that's captured in the system itself. So the more amplitude we have, the more energy we have in an oscillating system. We'll return to these ideas of equilibrium and amplitude further when we talk about waves. Right now, just realize that equilibrium and amplitude both occur in waves and in just oscillations, and we'll get through the differences between those two. And equilibrium is where your rest position, where you start. Amplitude's how far you move away from the start. And then you have that energy associated with your amplitude. The last thing I want to talk about in this W1 standard is the pendulum. Pendulum is contained within our W1. And I want to talk about what a simple pendulum is. That's the only type we're going to look at in this class. So we're not going to look at any sort of physical pendulums that are a little bit more complicated. A simple pendulum is defined as having a mass that's suspended from some fixed point by a light string or wire. The wire needs to be light, or the string needs to be light, so it doesn't affect the motion of the pendulum. If you have this condition, or if you have nearly this condition, they consider it a simple pendulum. When you talk about simple pendulums, they do undergo simple harmonic motion. That just means that they regularly oscillate above their central equilibrium position. And if we're talking about our simple pendulum, the only thing that affects the period of a simple pendulum is the length of the string, so how far the mass is from the pivot, and the acceleration due to gravity. On Earth, that doesn't change at our surface. So the acceleration due to gravity is pretty much constant. I suppose if you took a pendulum to the moon or to a different planet, or if you took it off the surface of the Earth and took it to the top of a mountain, you might get a little bit of a different period for the pendulum. But that being said, as long as the acceleration due to gravity are on Earth's surface, and that the only thing that's going to determine how long it takes a pendulum to go back and forth is the length of the string it's on itself. There's an equation. This is not in your Regents reference tables, but I do want you to know this equation, that there is an equation that determines the period of the pendulum, and you can find it. And it says that the period of the pendulum is equal to 2 pi multiplied by the square root of L over G, right? L being the length of the string and G being the acceleration due to gravity. On Earth's surface, the acceleration due to gravity is 9.81 meters per second squared. That number is going to be very important to us in the future. We don't use it a ton during waves, but just realize that this G is 9.81 meters per second squared, and that is on the front of your reference tables. So if you want to see what that G is, if you want to remember it, if you're answering a question that has that acceleration due to gravity, 9.81 meters per second squared, you could always find that on the first page of your reference tables. Let's do an example of this. This is using the equation we just looked at. We want to figure out what the length of a pendulum is that has a period of 0.700 seconds. So it takes 7/10 of a second for it to oscillate back and forth and go through one full cycle. We're going to use our equation. Period is equal to 2 pi square root of length of the string divided by g. G being 9.81 meters per second squared, and we're trying to find length. So I'm going to plug in some values that we know. We know t is 0.7 seconds, and we know g is 9.81 meters per second squared. In this scenario, you would just divide 0.7 by 2 pi, square what you get from that, and then multiply by 9.81, thereby isolating the L term that we have right here that we're solving for. And when you do so, you'll find that the length of the pendulum would be 0.7 seconds. Notice that in this one, I didn't specify acceleration due to gravity. If that's not specified in any particular example, it's safe to assume that it's just 9.81 meters per second squared. In fact, in this class, you could assume that you're on the surface of Earth for every question unless told otherwise. So here, acceleration due to gravity, 9.81 meters per second squared. There's one example I want you to do in the next slide about the period of a pendulum using that equation. So do that one, and then that should wrap up this first lesson.